Hello everyone, I'm Joe, a PhD student at Purdue University. Today, I'm excited to share our work on dynamic redirection for ETHD-based VR interactions. In this talk, I will introduce our novel strategy that enables smooth and safe interactions with both stationary and moving virtual objects. We want to let the user of a virtual reality application not just see, but also touch the virtual world. Here, without the haptic feedback, the user slices through the virtual disk. A promising approach is to rely on a robot to place a real-world object where the virtual object is. Such robots are called encounter-type haptic devices, or ETHDs. ETHDs have three important challenges. First, they have to be able to reach at many locations in the virtual environment. Furthermore, they have to do it quickly to meet with the user. Second, and maybe this should be the first according to Asimov, the ETHD should not hurt its human user. The user doesn't see the ETHD, so inadvertent collisions with the moving ETHD should be avoided. Third, robots are expensive. The farther the desired reach and the heavier the payload, the more expensive they become. We make the following contributions. First, we have developed an ETHD that has good reach for its cost. Our ETHD can reach anywhere in a 60 by 60 by 40 centimeters volume. Our second contribution is to incorporate safety concerns into a redirection strategy. Our redirection strategy enforces a non-negotiable safety rule. The ETHD is required to stop before the user makes physical contact with it. Finally, we have tested our ETHD and redirection strategy in a user study with good results. Here is an illustration of our redirection strategy that enforces safety. Consider a moving virtual disk that the user wants to hit with a stick. At first, the ETHD moves in sync with the disk. When the stick gets close to the ETHD stops for safety. The virtual disk continues to move, which creates a gap between the disk and the ETHD. Redirection is used to hide this gap. We make sure the virtual stick hits the virtual disk exactly at the same time as the physical stick hits the physical disk, carried by the ETHD. Here's the whole thing in real time. Our user study had two experiments. In the first experiment, the participant had to hit the stationary virtual object. The ETHD has to move to align with the virtual object. We had two control conditions and one experimental condition. In the first control condition, no redirection was used, so when the ETHD stopped early for safety, the virtual stick slices through the virtual disk. In the second control condition, we used the prior redirection approach that relies on a prediction. When the prediction fails, the same artifact occurs, with the virtual stick slicing through the virtual disk. The experimental condition uses our strategy, which enforces safety and maintains synchronization between the virtual and physical contacts. Here are the results of the first experiment. Delta is the distance between the virtual stick and the virtual disk. We want this distance to be 0. In other words, we want good visual alignment. Epsilon is the distance redirection has to hide. It's the gap between the virtual and real disks. As you can see, our dynamic redirection provides great visual alignment even for large epsilons. The differences are significant. Here are the subjective results of the first experiment. The participants were asked whether the contact was well synchronized in a 5-point Likert scale. 5 means perfectly aligned, while 1 means not aligned at all. As you can see here, with dynamic redirection, the participants were always able to feel appropriate contact, while with no redirection is the opposite. With static redirection, the robot can sometimes move the physical object to the target position, but not guaranteed. In the second experiment, the virtual object was moving. The ETHD follows along but stops when the user is about to hit it. In the control condition, the virtual disk stops when the ETHD stops. This guarantees contact synchronization, but the user might notice that the disk stops early before contact, and not as a consequence of the contact. Our dynamic redirection allows the virtual disk keep moving until contact is made. Here are the results of the second experiment. The x-axis tau shows the time between the virtual disk stopping and the contact. As you can see, for the control condition, no redirection, the participants can tell the disk stopped early even for tau value of 100 milliseconds. With our dynamic redirection, however, participants perceived the virtual and physical contacts as well synchronized. Our work focused on stick-based interactions. Paradoxically, the stick allows for more realistic haptic feedback in a wider range of circumstances. By hiding differences between the physical and virtual objects, it also improves safety by physically avoiding the user's body touching the moving robot. Haptic feedback for hand interactions presents greater challenges compared to using a stick. People tend to have more detailed expectations when an object collides with their hand rather than with the stick. The perceived impact is influenced by the object's momentum, which is determined by its mass and speed. However, it remains unclear whether a person's visual expectations of the impact affects the actual tactile perception. Understanding this relationship is crucial when transitioning haptic feedback from stick-based to hand-based interactions.